Algebra, Unit 3, Lesson 4, Direct Variation, Video 4. Direct variation equations. A direct variation is described by an equation in the form of y equals kx, where k cannot be 0. Now, you could be thinking y equals mx is what we normally do. When we're talking about direct variation, we're going to use the letter k instead. The equation y equals kx illustrates a constant rate of change, or a slope, and k is the constant of variation. So it's almost like the constant rate of change, the slope, is the constant variation, k. It's also called the constant of proportionality. So just some vocabulary words there for you. Name the constant of variation for each equation. Then find the slope of the line that passes through each pair of points using the slope formula. So we need to find constant of variation. So constant variation are k equals, we're going to start, as we look at the graph from left to right, we're going to start at this point and say, well, okay, so how many rise and run, or in this case, fall and run? It looks like 4 over 1. And the slope then, m equals 4 over 1. Letter B. Please try that one on your own. The slope of the graph of y equals kx is k. Since 0 equals k of 0, the graph of y equals kx always passes through the origin. Always passes through the origin. Always. Therefore, the x and y intercepts are 0. Always. This will always pass through both the x-axis and the y-axis at 0. So 0, 0 will always be a point, and this will always be, again, a linear function, so it'll pass through just once with a straight line. Graph the following direct variations. So notice that both a and b are in the form y equals kx, and they're always, so see, notice how there's no b, no plus b, no y-intercept given, so the y-intercept has to be 0. So both of these problems are going to start at the origin, so that's our first point. So now we have a slope, or a direct variation, a constant of variation of -6. So again, we're going to count up and over, so rise and fall. So I'm going to go up 6, 1, 2, 3, 4, 5, 6, and then since it's a negative slope, at the end of the day, this line needs to be going downhill. Negative slope, down the hill. So I'm going to go over 1. Now the only way to go over 1 would be to have to go to the left. And now I'm going over 1 because our constant of direct variation, or our slope, should always be a fraction. So really this is -6 over 1. So my second point is right there. Now if I try to go up 6 again, I'm going to run out of room. Don't add graphing lines. Don't make this coordinate plane any bigger. Instead, go the opposite way. So start back at your main point, and now go down 6 to the right one. So 1, 2, 3, 4, 5, 6, right one. There's your second or third point. So now we need to connect those with our ruler. So again, don't get lazy. Take out your ruler. We're going to draw a line between the 3 of them. We're going to add arrows on both ends. And we have graphed that constant of proportionality. We've graphed that linear function. Please try letter B on your own. The graphs of all direct variation equations share some common characteristics. Bullet 1. Direct variation equations are in the form of y equals kx, where k cannot be 0. The graph of y equals kx always passes through the origin. I can't say it enough, it always passes through the origin. The slope is positive if k is greater than 0, and the slope is negative if k is less than 0. So remember, positive up the hill, negative down the hill. On the back, write and solve a direct variation equation. If the relationships between the values of y and x can be described by a direct variation equation, then we say that y varies directly as x. Suppose y varies directly with x. Write a direct equation write a direct variation equation that relates x and y, then solve. Letter A, if y equals 15 when x is 12, find y when x is 32. So let's go back to our equation here. We've been now working with y equals kx. So I'm just going to substitute that stuff, the y and the x, and find k. So I almost like to think of this as a two-part problem. Y equals kx. So letter A, if y equals 15, so 15 equals kx. I don't know k when x is 12. So k times x is still x times k. So I'm going to write 12, the coefficient first, times k. I'm going to solve for k. So divide both sides by 12. And you are left with k equals 5/4. I just divided both sides by 3 there to reduce that fraction. Or you can use your calculator and get a decimal, your choice. So k equals 5/4. So part 2, use that, take it next door. So find y equals x. Find y when x equals 32. So I'm going to again start with the original. Find y. Don't know what that is. When x is 32. Well, k is 5/4. And when x is 32, so I'm going to substitute that in. Now I'm just going to simplify. Y equals, 32 times 5 divided by 4. I don't know that in my head, so instead I'm going to cross cancel. I can also put this over 1 if that helps you visualize that. So 4 and 32, 4 goes into itself 1 time. 4 goes into 32 8 times, so that reduces. So then my answer is 40 over 1, or just 40. So y equals 40. So find y. Y is 40. We're done. Please try. We'll do B, and then I'd like you to try C and D on your own. Letter B. Again, I'm going to start by dividing this in half, because it's almost like I have two problems here. Find x when y is 63, if y is 72 when x is 8. Okay, so find y when x is 63. There's one problem. If y is this, there's a second problem. So I'm going to start with the second half, because here I have too many variables. Again, I'm looking for y equals kx. So in this first portion of the problem, find x, I have two variables I don't know. So I'm going to skip that and head right to this section here. So y equals kx, so y is 72 when x is 8. I'm going to solve for k. So when I do that, I get k equals 9. Now I'm going to use that over here. So find x when y is 63. So y is 63 equals kx. So we had 9x. Divide both sides by 9. We get x equals 7. Find x, and we're done. So it may help you divide your problem into two. You need to start with the part of the problem that only has one unknown variable. You cannot start at the point where there are two. And then we're going to do letter E together. The distance a jet travels varies directly as the number of hours it flies. A jet traveled 3,420 miles in 6 hours. Write a direct variation equation for the distance d flown in time t. Estimate how many hours it would take for an airliner to fly 6,500 miles. So we need to go back and set up, so our y equals kx. So then in context of the problem, our distance varies directly with kt. So let's set that up, and again, if we need to think about it as two problems, go ahead and do so. So a jet traveled 3,420 miles in kt hours, and t is 6. So I need to find k, so or the actual speed now. So we're going to divide both sides by 6. So we get k equals 570. So it sounds like this jet is traveling 570 miles per hour. Okay, so write a direct variation equation for the distance d flown in time t. Done, we did it here. All right, so estimate how many hours it will take for an airliner to fly that many miles. So the time, we need to estimate the time. So it sounds like that is our unknown. Well, they want us to know 6,500 miles, and if we're traveling at 570 miles per hour, we need to figure out t. So we're going to solve for t, divide both sides by 570, and we get t equals 11.4 and some other stuff there. So if I was to round this, I would say t would be approximately 11.4 hours. And estimate how many hours it will take. It doesn't say where to estimate it, so I might keep it as 11.4, but because it's a word problem, I need to end it with about a sentence here. So it will take about 11.4 hours. Again, please try letter F on your own. Same way, if you need to divide it into two problems, go ahead and do that. Good luck.